Yeah, good afternoon to you all, audience. I wish you, let me use this opportunity to welcome you all to today's lecture as we continue from where we stopped yesterday. And today we are going to be looking at the section 4, which will span from today till tomorrow. So, of course, as we all know, that this lecture is a simple and ICTP research in pairs lecture on theory of partial differential equation that is coming to you live from CIRM here in Marcel Lomini. So, and today, as we all know, today is 29 of, sorry, there is a mistake here. This is supposed to be, it will be corrected. It should be 29 of May, not June, please. So, today we are going to be looking at the theory behind the boundary value problems. And of course, we will surely need the knowledge of what we have been doing earlier from the first order PDEs. So, this is section 3 that we discussed yesterday. Then we have, this is the section 4, which is the boundary value problem. What do we understand by a boundary value problem? Yeah, of course. Here, let's just look at this theory here. This says that if a second order differential equation, which is given here in 4.1, this is the general form of second order partial differential equation. We can see, but second order partial differential equation, we can see that the two independent variables here are x and y, and the unknown function here is u. And by the time we look at it, we will see that the derivative, that is the PDE here, are uxx, which implies di squared u, di x square, and uxy, which implies di u, which implies di squared u, di x, di y, and this, which implies uyy here, which implies di squared u, di y square. So everything here equal to 0. This is the general form of the second order partial differential equation. So it's to be solved within a specified region. Yeah, now that we are now talking about a boundary value problem, it means that we are going to be seeking the solution of this problem in a given region, or let's say space, in which the values of the dependent variables u are specified at the region boundary, dir. That is, the value for these independent variables u here will be specified at the boundary. So let's just assume that we have a space this way. Let's say we have something like this, and then of course, this is the boundary, or these are the boundaries rather. So here now the solution of this problem that we are going to be seeking is just going to be between this space here like this, and the value of the unknown function, which is u, will be given at this point and also at this point. So once we have these values, this will help us to determine the solution within this boundary. So these boundaries need not enclose a finite volume. In this case, one of the boundaries may be at infinity. Yes, there is possibility that one of the boundary could be at infinity. But of course, if it is at infinity, it's either a decay will occur or the function will continue to increase, depending on the kind of problem we are actually considering. So, and then a PDE in which one of the independent variable is time. The value of the dependent variable and often its time derivative at some instance of time t equal to 0, say, may be given. That is, if one of the dependent variable of the PDE we are considering has time, that means the PDE depends on time. And then often the value of this time at the what's equal is always given at t equals to 0. Then this type of condition are called the initial condition, which implies that what at the initial stage, u of t, that is u of t is equal, u of t is always given, maybe a, at t equal to 0. So this condition here is what we call the initial condition. Hence, the time boundary and initial conditions will be used as appropriate. Yes, if by the time we are seeking for the solution of this partial differential equation, of course, this initial condition that is given and the boundary condition will be used where it is appropriate in order to help us obtain the solution of the problem we are considering. Then we shall concern ourselves here primarily with two types of boundary conditions that arise frequently in the description of physical phenomena and which we encounter frequently in many applications. Yes, of course, PDE can depend on different kind of boundary, but here we'll only concern ourselves with the ones that we encounter almost on a daily basis. If we can recall, we say that as long as the saying that the only thing that is constant in life is change, then the study of partial differential equation will never be overemphasized because it has to do with changes, either depending on time or space. It can just be anything. The differential equation, I mean, the derivative itself is talking about change. So the first one here is the Dirichlet. The first one is the Dirichlet condition, where the dependent variable u, that is the unknown function, is specified at each point of a boundary in a region. For example, at the end of a rectangular region. Let's look at this. This is the rectangular region where a is less than or equal to x and x is less than or equal to b, and c here is less than or equal to y and y is less than or equal to d. So this is an example of a Dirichlet boundary condition. So if you look at it, you see that the independent variable here are x and y, and then the region is a is less than or equal to x and x is less than or equal to b. So that means x takes value between a to b. The same thing with y is less than or equal to, c is less than or equal to y, and y is less than or equal to d, which implies that the other independent variable, which is y, takes value between c and d. That's an example of a Dirichlet. Now, the Cauchy condition, if one of the independent variables is time, and the value of both u and u t are specified on the boundary at time t equals to 0, that is at some initial time, then this condition is referred to as a Cauchy type. So supposing we also have t, that means the PDE we are considering also depends on time. Then it also depends on time, and it is both specified at u and the derivative with respect to time. Then we say that this condition here is of Cauchy type. So in applied mathematics, physics, and engineering, PDE generally arise from the mathematical formulation of real-life physical problems. Yes, PDE in most cases we use them to formulate a mathematical representation of a real-life situation. That is what we use PDE often for. And these usually arise in applied physics, applied mathematics, physics, and then engineering. Engineering generally is all about mathematics, all about applied mathematics. So the process of determining a PDE subject to imposed boundary condition is solving a boundary value problem. Yes. Now, for us to determine the process of determining a PDE subject, now for us to obtain the solution to a given partial differential equation with an unknown function u is for us now to solve what we call a boundary value problem. So which implies that by the time we have a differential equation and attached to it, we have some boundary condition. So the differential equation with the boundary condition together is what we call the boundary value problem. And it is initial value problem if the conditions are imposed on the differential equation. Now, for us to solve this differential equation or this partial differential equation, we are going to be looking at the method of separation of variables. This is perhaps the oldest and commonest method of solving partial differential equation. Yeah, today we have a lot of methods that can be used to solve a partial differential equation. In fact, every day, different methods continue to come up for solving partial differential equation. But the common one and the oldest one is this method of separation of variable. And the reason why we continue to have this new method, most especially in numerical, is because our daily problem are becoming more and more complex. That by the time we model the problems, in many cases, we will not be able to obtain the solution to that problem. Thereby, we will not be able to do any analysis of the given formulation. So this gives rise to the development of more and more methods to handle this complex partial differential equation. Sorry. So this perhaps is the oldest and commonest method.
Please.
The door.
You are still to close the door.
Yeah. Yeah, thank you. Yeah. So, given the unknown function u, which is here in 4.2, this function, we shall on the onset make some fundamental assumption, thus that u of x1, x2 to xm is equal to x1 of x multiplied by x2 of x2 till we get to xm of x1, which is given here in 4.3, in which xk implies xk of, that is, what we are saying is that x1 is the same thing as x1 of x1. So this is what we are going to be making use of. X1, we take it as this, so that is what that is trying to tell us, that xk is the same thing as xk of xk. So in which this then a function of a single independent variable. Now on substituting 4.3 into 4.1, that is, we are now going to substitute, by the time we assume this general solution here, that is this 4.3, we are now going to substitute it into 4.1, which is the differential equation. And simplifying, we obtain ordinary differential equation. By the time we simplify and then we substitute, we are going to see this by the time we start solving some examples. We see that the PDE will now reduce to ODE. And of course, we know that once we are able to reduce our PDE to ODE, then it is easier to obtain the solution. So, and simplifying, we obtain an ordinary differential equation in the unknown function xk, where k takes value from 1 to m. Then some of the boundary condition of the original PDE will give rise to corresponding boundary conditions to be satisfied by some of the functions xk. Then we will therefore have to solve the m coupled or uncoupled, because by the time we resolve them into ODEs, we are going to have uncoupled ordinary differential equation, some of which may be boundary value problems or initial value problems. This particular solution, x of k, are then used to constitute the most general solution of the original PDE. So let us consider the PDE in two independent variables, x and y, in this form of 4.5. This is one of the type of differential equation that was discussed in our last lecture. Supposing the solution 4.5 is given as u equals to x of x and then y of y. Yeah, of course, we say that what? That differential equation depends on x and y. So we are now going to assume two functions, or the product of two functions. We are going to assume the solution of the unknown function to be the product of two functions, which depends on the independent variable each, in which x and y are functions of x and y respectively, and u is the dependent variable, or we call it the unknown function. Then substituting 4.6 into 4.5 and simplifying, we are going to obtain what we have here, which is these are 4.7, where f of d and phi of d prime are quadratic function of d. Of course, we know that d here is d dx and d prime is d dy respectively. So we observe that the left-hand side of 4.7 is a function of x only, while the right-hand side is a function of y only. And the two cannot be equal except each is equal to a constant. It could be minus, it could be negative, anyone. If we look at this 4.7 very well, we'll see that this equation on the left-hand side only depends on x. This one on the right-hand side only depends on y. And the two of them cannot be equal except if we assume that the two of them are equal to a particular constant, which we assume to be this minus lambda. Thus, we assume them to be equal to minus lambda. So by the time we assume everything to be equal to minus lambda, so each one, f of d of x of x will be equal to this, and phi of d prime dot this will also be equal to this. Then the solution of 4.5 therefore reduces to the solution of 4.8. So we are now going to solve the differential equations independently. We solve here to obtain our x of x. We solve this to obtain our y of y. So the usefulness of the solution of PDE is quite limited because of the difficulty in choosing the appropriate arbitrary functions that will satisfy the imposed boundary condition. This is, however, eliminated for some class of PDEs, which is usually linear, by certain techniques, one of which is based on the principle of superimposition of solution. So this states that if each of the m function z of x satisfy a linear PDE, then an arbitrary linear combination, which is given here in 4.9, where alpha k takes the value from k equals to 1 to m are constant, also satisfy the differential equation. The combination of the method of separation of variable and the superposition of solution is usually known as the Fourier method. Now, let us look at this example here. This first example here says that solve by the method of separation of variable the differential equation this. Now, how do we handle this differential equation? Now, the first thing, as we said, is that what? We are going to assume a solution x and y, because if we look at this, the first thing, let us identify the independent variable. The independent variable here are x and y, and the dependent variable is that is the unknown function here is u. So now it means that we are now going to assume two functions, which is x of x and y of y, and then we assume their product to be the solution of u of x comma y, which must not be equal to 0. Now we are now going to differentiate this. From here, we are going to differentiate. We are going to look for di u di y, di u di x, and di squared u di x square. Then we substitute it into this. Differential equation. Immediately we substitute it into that differential equation. Then the next thing we are now going to do is to divide through by these x of x, y of y. So this is what we are trying to say in essence. That is, we have we assume the solution of u of x comma y. These are the two independent variables as x of x. Then we have y of y. So this is what we have now. And this is the differential equation here. So we are going to look for this component here. Now, what is our uy is just going to give us x y prime, and ux will give us x prime y, and uxx will give us xxx y. Then we now substitute all this into this differential equation. By the time we do that substitution, this will give us x prime prime y. Then the next one, which is minus 2, which we have di u di x, which is this. So we have x prime y. Then we have plus di u di y, which is plus x y prime. This is what we have. And then we assume, and then we say the whole of this is equal to what? Is equal to 0. Then by the time we divide through by this, we are going to divide through by what? We divide through by xy. We divide this by xy. We divide this by xy. So by the time we do this, we will see that this will surely go with this. This will go with this. This will go with this. And then this differential equation now will now reduce to x prime prime divided by x minus 2x prime divided by x. Then we have plus y prime divided by y, and everything here is equal to 0. So this is what we have as the differential equation. Now we can now rewrite this as x prime prime upon x minus 2x prime upon x to be equal to minus y prime upon y. So by the time we look at it now from here, that is what we have here now. So you will see this is where we are now. So you will see clearly, yeah, of course, we can rewrite this as 1 upon x in the bracket of x prime prime minus 2x prime to be equal to minus y prime upon y. So here now we'll see that if you look at this differential equation, you see that what? On the left-hand side, everything here depends on x. On the right-hand side, everything here depends on y. So the next thing we are now going to do, and then we say that, of course, the two of them cannot be equal to what? They cannot be equal to 0. So here now, but rather we say that what? They can only be equal to, let's say what? A lambda. So here now, we can say everything here is equal to a constant. And let's call that constant lambda. Let's say it is lambda. So we're now going to equate each and every one of them to lambda, which means we equate this one to lambda, which is 1 upon x prime prime in the bracket of minus 2x prime equal to lambda. And then we have minus y prime upon y also to be equal to lambda. Then we can then cross multiply. By the time we cross multiply, and then we rewrite the differential equation. So this will just multiply this, so that we have the first equation will be x prime prime minus 2x prime. Then we have minus lambda x. Everything will be equal to 0. Then this one is going to give us y prime plus lambda y also equal to 0. So this is how we obtain these differential equations. So the next thing is we now solve each and every one of these differential equations. So this corresponds to what we have here. You can see we know that this d here is di x. I mean, d is di x and d prime is di y. So this differential equation corresponds to this. So we can now use our earlier method that we know to solve these two differential equations. And on solving that, for x of x, this is what we have at the solution, and for y of y, this is what we have at the solution. So the solution to that differential equation, u of x comma y, is now going to be the product of these two differential equations, which is what we have in here. And then this one is just the constant. We merged all the constants that appear together because we have a constant c here. So by the time this equation multiply this equation, we are going to have this a to multiply this c and this b to multiply this c. So we can just put them together as d equals to ac and e is equal to bc, and that is how we obtain the solution. And these are arbitrary; they are just arbitrary constant, because by the time you multiply a constant with a constant, you are going to obtain another constant. Now, the next thing now is let us now look at another problem here. This says that determine the solution of the 3D wave equation given here. This is the wave equation that is given in this place. You can see that here now, this differential equation here depends on time. You can see we have time here. And then this one, of course, we know this one is just the Laplacian of this u. But here now we are talking about 3D wave equation. So this Laplacian here now is, of course, this is just di xi plus di yj plus di zk. So the Laplacian of this will be equal to di x all square plus di y all square plus di z all square. This is what we are going to have by the time you expand this Laplacian. So by the time you now bring the independent variable, then the differential equation itself will now be this. So the differential equation, okay, yeah, this is the Laplacian. So here now we say that we have c square, then it will now be in the bracket of the Laplacian of u. So that means we are going to have this should be the differential equation, please. Sorry, the x square, the y square, the squared, the z square. So that by the time we are talking of Laplacian, sorry. So here now, we are going to have our c squared to be in the bracket of the first one, which is di squared, di u squared, plus di squared u. Then we have di y squared plus di squared u. We have di z squared. So this is what we have. Then we can close this, and everything here is equal to di squared u. Then we have di t squared. So this is what we have. This is the differential equation we are considering here. This is the 3D wave equation. So here now, if we now look at it now from what we have written here, we'll see that we have up to 4 variables or 3 space variable and time. So here, what we are going to be assuming is now going to be 4 functions. Now look at it. From what we have here, we have one of the independent variables as x, y, z, and then we have time. So here we are now going to be assuming 4 sets of functions. The product of these 4 sets of functions will now be the assumed solution of the independent variable u, or of the unknown function u. So here now, we are now going to assume the solution u of x, the solution u of x, comma y, comma z, comma t to be equal to x of x multiplied by y of y, then multiplied by z of z, then we have multiplied by t, which is at the time, t of t. And we say that this must not be equal to what? Must not be equal to 0. So the next thing we're now going to do is we now differentiate this in order to obtain all these components. So here now, of course, we know that our di squared u di x here will mean differentiating the whole of this twice while keeping all other ones as constant. The same thing goes with this, the same thing goes with this, the same thing goes with time. So by the time we do that, this is what we are going to obtain. Then we then divide through by u as we have been doing. By the time we do that, then this is what we are going to have as the differential equation. We can see that this one depends on x, this on y, this on z, this one is what? Is just on t. Then by the time we cross multiply with this c, we are going to have this equation. So here now, what we are now going to do here now, now say that this equation is true only if each of the component part is equal to a constant. Yes, we are now going to assume everything here to be equal to what? A constant. So by the time we do that, we are going to assume, now we assume this one to be minus p square, this one minus q square, this one minus r square, and then this one minus s square. That is what we do for each and every one of them. Now, by the time we do that, then we can now resolve each one into a differential equation. Let's just take the first one that was resolved, x prime prime. We say that x prime prime divided by x is equal to minus p square. So this will give us what? X prime prime to be equal to minus p squared x. So we have x prime prime plus p squared x to be equal to 0. So this is how we are going to resolve for all of them. And by the time we do that, that will just give us what we have here in this equation 6. Then we then solve each and every one of these equations. On solving each and every one of these equations, we are going to obtain this as their solution. So if you look at it, this one actually depends on t. That is why you see it is having a t dot dot to show that its own variable, its own independent variable is what? Is a time, not a space like these other ones. So these are the solutions to these differential equations. They are the ones we have here in equation 7. So the next thing now we are now going to do is, since the parameter p, q, r, and s are dependent by virtue of 4, we may express t of t as what we have here. Then hence, by virtue of 1 and 7, we thus have that the solution u of x, comma y, comma z, not tt, comma t is equal to what we have here. You can see is now going to be the product of all this. And by the time we do that, that was just the most general solution thus is now going to be given as what we have here, in which the function this is z, not t, please, as defined in 7 and 6. So that is the general solution for that differential equation. Now let us now look at this. This is a solution of a 3D Laplace equation in a curvilinear coordinate system. Yeah, the first differential equation here is the cylindrical form of the 3D Laplace equation, and this second one is the spherical form of the 3D Laplace equation. So in this section, we will solve the problem for the spherical, this one that is more complex. Then the solution for the cylindrical coordinate follows the same procedure as this. This one has more complex solution because it's bigger, but the solution method is the same. So And then the corresponding differential equation is given by what we have here. That's for the spherical. Yeah, of course, if we look at it very well, let us now identify the independent variable. And you can see that these are the independent variable here. We have R, then we have these, let's say, theta, and then we have these, what is it called, this file here. These are the independent variables. So that means we are going to assume, using the separation of variable method, we are going to assume 3 different functions, which are what we have here to be the assumed solution. This is what we have here. Then we cannot differentiate with respect to R, with respect to this, then with respect to this phi. And on doing that, that will give us this differential equation. By the time we divide through by u of R, comma theta, comma phi, this is what we are going to have there. We see that this cannot be equal to 0, but rather they can only be equal to what? A particular constant. So by the time we do that, now if we now look at it very well, we are separated, then we see that these ones, all these ones here, depend on R and these theta, while this one only depends on what? On phi. So we can now separate them from here. Now, again, by the time we separate them, we equate this, the right-hand side, to this, then to a constant, which we call m square. So by the time we separate them, we are going to have this, then we are going to have this as the second equation. Then again, we are now going to again separate this again. That is, we are going to now separate R and this theta. Also, for us to do that also, that means we are now going to assume another constant. So here now, we now assume each side is a constant of this. This condition gives rise to the following uncoupled ordinary differential equation. So by the time we equate it to this, we choose this as our constant, and then we equate it to this, then we are going to have these 2 differential equation. Now, for us now to solve this differential equation, or for us to reduce this differential equation, we assume our cos theta here to be equal to mu. Then, of course, we know if we assume, we know that our cot here is 1 all over tan, and we know that our tan theta itself is sin theta all over cos theta, which means that this cot theta is cos theta all over sin theta. So from what is it called? From Pythagoras theorem, we can always resolve this to obtain the value for this cot theta and also the value for this sin theta here. And on resolving that, we are going to have this as the differential equation. Now, and then equation 10 is associated to legendary differential equation. Yes, by the time we look at it, it is in the form of the legendary differential equation. So solving 4 and 5 and x in standard form, this is what we obtain as the solution. This and this and this. This for the second one, this for the second one. I mean first, second, and then third solution. Then the next thing is now to obtain the general solution, which is u of R, comma theta, comma phi, and everything will give us this by the time we obtain the product of the 3 functions. So that is what we have. Then the arbitrary constants are chosen in a manner that the solution is bounded. This implies that this f here is equal to 0. Therefore, q cos theta tends to infinity as theta tends to 0. Consequently, the general solution again can be given as what we have here. And then a solution of the problem in the form of this, that is in form of 6, 7, and 8 are called the special harmonic, while the solution in the form of this also can also be called plane harmonic. That is excluding this one. The 3 of them can be called special harmonic, but these 2 also can also be called the plane harmonics. So that is how we have that. Then now the next one now is a solution of 3D wave equation in curvilinear system. Now, also the wave equation here is also given in terms of the cylindrical and the spherical. So just before we move forward, we can follow the same process that we have followed in this place to solve for the cylindrical of this problem. So here now, let us look at the 3D wave equation in curvilinear coordinate system. So here we have the cylindrical form, and then we have the what? We have the spherical form. So now here in this section, we will solve the problem for the cylindrical coordinate system, then the spiral case follows the same procedure. The same thing, this is the differential equation here. This is the PDE we are considering. Then assume a special, assume a separable solution of this form. Yeah, of course, we are going to identify the independent variable, which is r, theta, and z. And then we are now going to assume a solution for this. Of course, this also depends on time. So that means we need time here, which is this. And this must not be equal to what? It must not be equal to 0. So now, this is what we have. Then we can now differentiate this with respect to each and every one of these variables. And then we substitute back into this differential equation. And on doing that, this is what we are going to have. Of course, all these ones here depends on space variable, while this one depends on time. So the left-hand side of this is a function of r, theta, y. The right-hand side is a function of t, yes, as we have said earlier. Then we can now equate all of them to what? To their respective constant. That is what gives rise to this differential equation, this differential equation, then this differential equation, and then this. So from here now, we can now talk about the solution. And then here we can see this is the solution to all the 4 differential equation. But here now we are now talking about, what is it called? We are talking about the Bessel function. So that's what we have there. Then the next thing, the general solution. Now, of course, as we know, we are now going to bring them together. We are going to obtain their products. And then on doing that, that will give us this solution that we have here. Then therefore, the final solution can be given as what we have in here. By the time we continue to reduce what we have, because there is a lot of mathematics in between, a lot of a kind of reduction that needs to be done for us to obtain what we have here. Then these are so this is what we have for this problem here. So you are all welcome back. So let's just continue our discussion. We will soon round up on this particular topic, which is the boundary value problem, so that by the time we meet tomorrow, we will now be talking about tomorrow, which is going to be our last day. We are going to be talking about one very special method of solving advection equation. And this method is nothing but the characteristics mapping method. This method is actually an advancement on the characteristics method that we discussed at the beginning of this course. So that method, we may not be able to say all the steps that are involved because it is very, very complex. But of course, we are going to introduce you to the software where this method has been documented in GitHub. You can easily access it, use it to solve your problems, as long as your problem conform with the advection equation. So let us just quickly round up with this so that we'll look at, let us look at the next example here. This says that obtain the solution of the transverse equation, which is bounded by a circle of radius a, described by the function u of r, theta, t, satisfying the wave equation, satisfying the condition, again, u of a, theta, t equals to 0, u of r, theta, 0 is equal to f of r, theta, and then u t, which is the u t of r, theta is equal to phi of r, theta. So if you look at this very well, we will see that this boundary condition that is given here is the Cauchy type of boundary condition, because if you look at it, you will see that we are given a condition with respect to the u t here. You can see it here. The initial condition here is given here as what? The u t is equal to r, theta, 0. So now, solution. The initial boundary value problem is presented by what we have here. This is the problem, and these are the conditions that are attached to this problem. Yeah, of course. The first thing we are going to do, as usual, using the separation of variable method, is to identify the independent variables, which are r, theta, z, and then the time here. So by this, we know the number of a function we are supposed to assume in order to obtain the solution to this problem. So we can see here, these are the functions here. Of course, they must not be equal to 0. Then again, we now differentiate these and then substitute into the given differential equation as we have been doing, so that we can obtain all these differential equations. We can see them here. Then the next thing is what? Then we assume a constant and then we solve those differential equations. And on solving those differential equations, we are going to obtain these solutions. You can see them here from this equation 9 here. You can see, equation 10 rather, you can see them. Then we have the equation, what is it called? Is the standard Bessel. That is, after solving that is what we are going to obtain. Then since the solution must remain finite everywhere, we observe that ym here tends to infinity as r tends to 0. And also, of course, f of lambda is equal to 0. Therefore, we have this equation 7b here. Thus, u of r, theta, t is now equal to the Bessel function of this. This is what we have here, in which this is given as this, and b prime lambda here is equal to what we have in here. Then we recall that from now, we are now going to start applying those conditions. Of course, from the condition we have it that u of a, theta, t is equal to 0, and we have minus pi. This is the region of this variable, you can see, and then at t greater than or equal to 0. That means when time is greater than or equal to 0, from t equals to 0 upward. And then so here now we have this to be equal to 0. That is, we have r of a to be equal to 0. Therefore, this equal to, that is, if the whole of this is equal to 0, then it implies that this r of a is equal to 0. This is equal to 0 implies that u of r, theta also is equal to 0, which is trivially. And then we have the Bessel function of lambda a also to be equal to 0. So this is an eigenvalue problem with infinite solution. So supposing this lambda k now are the positive root of equation, this is equation 14, then the general solution becomes what we have here in equation 15. That's what we have here. That's the general solution. Then axisymmetric solution, this is the case where u is independent of theta. That is, supposing the supposing this u here, which is the unknown function, is independent of theta, then we have this solution in which lambda k here are the positive root of the Bessel function, which is equal to 0. So in view of the boundary condition, we have our u of r, theta, 0 to be equal to what we have here. So this is Fourier Bessel series. And to obtain the coefficient of a, that is to obtain this constant, we have this integral here. So we can see that. Then, of course, on carrying out that integral, we can see this, we have this. Then by the time we integrate this is what we are going to have. Then we recall also that this JP here will give us what we have here. That is the Bessel function of this. That is the integral of rj naught all square will give us what we have here, the r, which is equal to a square divided by this. And then we have, by the time we carry out this simple arithmetic, what's it called here, we are going to obtain what we have here. So, and then we have this. Then from the initial condition, again, we are going to be applying all the initial conditions to be obtaining all the constants. So here now, again, from the initial condition, we have it that the u dt, that is the derivative of the solution, at t equals to 0, at time t equals to 0, is given as this function, where we assume this function to be what we have here. So here now, we are going to make use of this for us to obtain the constant that is involved. So also, by the time we carry out all the integrals and all the words equal, we are going to obtain our constant, which is bj here, to be equal to this. So on integrating this will give us the exact equation that is representing this vj. Therefore, this what is it called is the solution of for radially symmetric wave with coefficient defined in these equations. So we are going to stop here, and tomorrow we are going to take, as I said earlier, tomorrow we are going to look at the problem of transport equation using the characteristics mapping, which is an advancement on the characteristics method. That is the Monge's method that was discussed in this course. And that tomorrow we are going to use 1 hour for that. Then we are going to use the remaining time for we are going to do a revision of everything we have done. Then we are going to take questions from each of the section. Then we round up the course by tomorrow. So we stop here for today. Thank you all for participating in today's course. Thank you very much. We see tomorrow.